Hello everyone, it's Dave Giles here for the next lesson of Cambridge International Education IGCSE Physics, Unit 3, Waves, and today we are looking at refraction. So, first objective is describe a link between angles of incidence and angles of refraction, calculate the refractive index of a material, and explain how waves change when they refract. So, let's get into refraction. So, material which light passes through, such as glass or air, is known as a medium. If an incident ray enters glass at an angle, then it is refracted and bends towards the normal. This is a normal line, similar to what we looked at in reflection. The only difference is you have a normal line, it's still at 90 degrees, but you have it going into the glass. So this is light passing through a glass block in this example, or plastic, or something along those lines, something that is transparent. So this is the angle of incidence, and this is the angle of refraction. It is then incident here. So we call this I1, and we call this R1, so that's incidence and refraction. It's incident here. So this is incidence 2 angle, and it's refracted out because it's changing speed. So when light leaves the glass, the opposite happens, it bends away from normal. So here, you've got light coming in at its usual speed of 3 by 10 to the 8 meters per second. It then slows down in here and then moves towards the normal. This angle here, I2 and R1, should be the same. And then it'll leave at the same speed as entered. So it'll leave with R2 being the same as I1. And it will bend away from the normal here. So to add normal lines and measure the angle of incidence, normal line, I1, R1, I2, and R2, just to summarize it again. So here I1 is 47 degrees, R1 is 28. This angle and this angle are the same, so I2 is 28 and R2 is 47, the same as I1. Now, quite often you'll do a practical with refraction, and you'll get a glass block. Oops, sorry, go back. You draw around the block and add normal line using a protractor. You'll measure various angles. So you might start at 20, put a little dot on here. Normally be a thin dot because a thin dot is easier, better for measuring. Well, I've done it big just so you can see it. Shine the light through 20, so make sure it goes through that dot, which you can just about see on here. Might be very clear. And then have it going through the normal as well. Mark where it comes out. Put a few dots here and join them up after you've moved the block away. Draw a normal line where the light leaves the block and measure your angles. You can join the two lines up in the middle. So I've used a green pen here just so you can see the difference. This is the one I've added after I've drawn these. And I can label this I1. So the light was shining from the bottom here. R1, I2, and R2. And these are the sort of typical results you might get when you shine the light into a glass block. So, does refraction cause changes in the following? Amplitude, direction, frequency, wavelength, and speed. So amplitude is no, that stays the same. Direction is yes, because when it moves from air to water, it'll refract towards the normal. Frequency, no. Wavelength, yes. And speed, yes. So the refractive index is the amount the speed of light changes by in a medium. So the refractive index is speed of light in a vacuum divided by speed of light in a medium. So speed of light in a vacuum is about 3 by 10 to the 8 meters per second. You will be expected to know 3 by 10 to the 8. You don't need to know this many significant figures. So the refractive index of a vacuum is speed of light in a vacuum divided by speed of light in a medium is a vacuum. So it's going to be this number divided by this number again. So it's going to be 1. Air is almost identical. And water and glass. So what this means here, glass, it's about 2/3 the speed of what it is in air or a vacuum. I'll let you calculate diamond yourself, give you a few seconds just so you can make sure you're comfortable doing the calculation. You should get about 2.4 for the refractive index of diamond. Moving on. So the refractive index can also be written as sine I over sine R. So, for example, to calculate the refractive index of water, we've got angle of incidence 63, and it's refracted at an angle of 42 degrees. So it'll be sine 63 divided by sine 42. Check you're okay, type that in your calculator, and should get about 1.33. And then calculate the speed of light in water. So we've got a refractive index of 1.33. And we know the speed of light in air is 3 by 10 to the 8 meters per second. So I've rearranged the refractive index with the letter N to get, I've got it as speed of light in a vacuum divided by speed of light in a medium. The medium being water. Rearrange the formula. So 3 by 10 to the 8 divided by 1.332. And you get 2.25 by 10 to the 8 meters per second at the speed of light in water. So, very quick task, find the refractive index of diamond to 4 significant figures based on the values here. So, sine I over sine R, sine 69 over sine 23, 2.389. So, a couple of quick questions. Monochromatic light may be characterized by its speed, frequency, and wavelength. Which of the following quantities change when monochromatic light passes from air into glass? So we know the speed changes. We know the wavelength changes. The frequency does not. So the answer is B. And the diagram shows a ray of light traveling in air and incident on a glass block of refractive index 1.5. What's the angle of refraction in the glass? So, give you a few seconds to try it yourself. You can pause it. First thing you have to realize is that is not the angle of incidence here. That is because the angle of incidence between the normal line and the incident ray. So the angle of incidence, add the normal line in here, is 55 degrees. And then N, refractive index is sine I over sine R. So sine R is sine I over N. R is therefore inverse sine of sine I over N. Put my numbers in, and I get 33.1 degrees here. Right. Okay, so what's happening here? You can see the straw going into a glass and it appears to bend. And that again is due to refraction. So as the light crosses the boundary between fluid and glass, it is bent, producing a distorted image. This is known as refraction. Spear fishing has been used for centuries and is still practiced by some communities. To accurately spear a fish, fishermen learn to aim a short distance behind the fish's image in order to compensate for the effect of refraction. So they're not aiming where they see the fish, they aim a short distance behind where they see it, because that's where the fish actually is. A little sort of analogy to show that is a car traveling through the mud. Now, if it's going straight through, it'll slow down through the mud, but it's not going to change direction. However, if it goes through at some kind of angle, then it is refracted. So if you look here, this wheel is going to reach the dirt or the mud first. As a result, this wheel is going to slow down and it's going to have like a turning effect. So this wheel's going slow, this wheel's going fast, so it's going to bend this way towards the normal, which causes the path to bend. And we're going to have a look at refraction in a ripple tank or in water. So you can see here, it changes speed when it goes from deep water to shallow water. When the plane wave passes from deep to shallow water, the wavelength becomes shorter. The speed decreases, the frequency remains unchanged, and it bends towards the normal. So when it gets shallower, think slower speed, shorter wavelength, and towards the normal. So we looked at wave fronts before. So the distance here, it's moving, so it's a bit hard to point out, but the distance between this peak here and this one here, that is the wavelength. This here is the normal line. So normally it'll be dashed. That's a solid line here though. And you can see that it's hitting at, say, 45 degrees. I haven't measured it. And when it goes from deep to shallow, it's going to bend towards the normal. So it's going to bend this way. Okay. So drawing wavefronts, two key aspects. Directions change and the wavelength changes. So you can see here, this is the wavefront, normal line, bending towards the normal. And you see the wavefronts are closer together, which means the wavelength has decreased. And when it goes the other way from shallow to deep, it's going to move away from the normal. And the wavelength is going to get bigger. As you can see here, this wavelength here is bigger than this one. Okay, so let's have a look at some paper 2 multiple choice questions. A water wave moves quickly into deep water. The wave now enters shallow water and its speed decreases. Which row shows what happens to the frequency of the wave and what happens to the wavelength of the wave? So if we look back at what we said earlier with what is changing when refraction occurs, so we said that the frequency does not change, but the wavelength does change. In this case, it's decreasing because it's going from deep to shallow. So remember, shallow decreases. Okay. Which diagram show, the diagrams show water waves that move from more slowly after passing into shallow water. Which diagram shows what happens to the waves? So they're going to change direction. So we can straight away rule out A and D. And when they slow down, they are going to move. So when they slow down, so they're going from fast to slow, they are going to move. Sorry, pardon me. They're going to move away from the normal, so towards the normal. So the answer is C. Okay. And the next question. The diagram shows two sets of wave fronts in a ripple tank. The student makes two statements about the waves. When the waves reflect from the barrier, the direction changes, but the wavelengths remain the same. He also says, when the waves reflect as they refract as they enter the shallow water, the direction remains the same, but the wavelength change. So which statements are correct? So let's go through statement 1 again. When the waves reflect from the barrier, the direction changes, but the wavelength remains the same. That is true. So we know D is not correct, and it can't just be 2 either. When the waves refract as they enter the shallow water, the direction remains the same, but the wavelength changes. Well, the direction is going to change. When it goes shallow, it's going to change direction. So therefore, only statement 1 is correct. Okay, and that's all of the multiple choice paper 2 questions. Join me again soon for the next lesson, which will be on total internal reflection, which I'll be uploading very soon, and I will post a link in the description. Thank you very much, everyone. I'll see you later.